Before completing 2 months of travel toward Mars, astronauts aboard any spacecraft using today's available propulsion systems will have already absorbed more radiation than the maximum lifetime limit considered acceptable for a worker professionally exposed to radioactive environments. And they are still in the middle of interplanetary space, having arrived nowhere. This figure is not a theoretical estimate. It is a measurement taken by scientific instruments aboard unmanned missions that traveled exactly that same route and recorded the radiation dose across every single day of the journey. The space between Earth and Mars is not empty in the way that word implies. It is threaded by 2 distinct categories of radiation that the human body is not equipped to tolerate under prolonged exposure, and together they explain why whoever travels to Mars may never return. That is not a provocation. It is physics applied to biology, and the answer is far more vast and far more disturbing than anything science fiction has ever managed to imagine. The first threat is the solar wind, a continuous stream of charged particles unleashed by the sun. Under normal conditions, a spacecraft's shielding offers partial protection, but the sun is unpredictable. During high-intensity events, known as solar particle events, it releases within minutes a surge of energy capable of driving radiation doses to levels that would cause severe cellular damage to any organism without adequate shelter inside a specially reinforced module. The second threat is far harder to combat because it has no local origin and cannot be deflected by any practical shielding. Galactic cosmic rays are extraordinarily high-energy particles traveling near the speed of light, born from supernovae and other violent events scattered across the galaxy, some of them billions of light-years from Earth. These particles pierce centimeters of solid lead without any meaningful loss of speed, and as they pass through the human body, they deposit energy along microscopic tracks that shatter DNA strands, cut through brain tissue, and damage cell membranes, leaving trails that the body's natural repair mechanisms can correct up to a point, but which, accumulated over months, overwhelm that capacity in a manner that is both progressive and irreversible. On Earth, 2 natural filters neutralize the vast majority of this threat without us ever having to think about it. The planet's magnetic field, generated by the rotation of a liquid iron core at its center, creates an invisible bubble stretching tens of thousands of kilometers around the Earth, deflecting the overwhelming majority of charged particles before they ever reach the atmosphere. The atmosphere itself does the rest. A column of air with a density equivalent to 10 meters of water above every square centimeter of the surface, capable of absorbing and scattering whatever the magnetic field failed to deflect. Inside a spacecraft in interplanetary transit, you have neither of those 2 filters. Instruments aboard missions to the Red Planet measured the radiation dose during transit at approximately 1.8 millisieverts per day, totaling around 370 millisieverts over 7 months of travel, equivalent to more than 3,600 chest X-rays performed over that same period. More than double the annual limit established for workers in monitored radioactive environments in any country on Earth. The problem does not disappear when you arrive. Mars lost its global magnetic field approximately 4 billion years ago, when the core that generated it cooled and the convection sustaining the field came to a halt. Without that shield, and with an atmosphere whose surface pressure equals what exists at roughly 35 kilometers of altitude here on Earth, too thin to filter radiation in any meaningful way, the Martian surface lies exposed to the same cosmic bombardment as open space. Add to that ultraviolet radiation, striking directly with no ozone layer to filter it. Every single day lived on Mars adds to the dose already accumulated during the journey. A complete round-trip mission, 7 months of transit, 13 months on the surface waiting for the orbital return window, plus 7 months of travel back, would deliver a total dose exceeding the limits calculated as the maximum acceptable for an astronaut's entire career, consumed in a single mission. Beyond that, the orbital window that makes the return journey fuel viable only opens once every 26 months, dictated by the relentless geometry of Mars and Earth's orbits around the Sun. You cannot simply decide to leave when you want. You are trapped not by walls, but by... And while you wait, the body continues tallying its silent reckoning. Gravity is invisible to those who live within it. We do not feel its constant weight upon our bones, our muscles, our cardiovascular system, because it has never vanished for a single moment in all the evolutionary history that shaped us. The human skeleton carries the density it does not as an excess of caution, but because Earth's gravity imposes a continuous mechanical load that bones must resist in order not to yield. Muscles carry the volume they do because they must move and support the body against that constant pull. The heart and blood vessels were calibrated across tens of millions of years to pump blood in specific directions relative to the gravitational field, with automatic reflexes that take as a basic assumption the fact that bodily fluid will always drain downward. When you remove gravity, as happens inside a spacecraft in interplanetary transit, the body begins to dismantle these structures because the stimulus that sustained them has vanished. Not as an accident or a failure of the organism, but as strict evolutionary logic. Structures that cost energy to maintain and are no longer being demanded are, from a biological standpoint, superfluous. In microgravity, bones lose density at a rate of roughly 1 to 2% per month. In the regions that bear the greatest load on Earth, the lumbar spine, the hips, and the femurs. To grasp what that rate truly means, in comparable terms, a menopausal woman without treatment loses an average of around 1% of bone density per year. And that process is considered a serious medical condition, demanding immediate intervention to prevent future fractures. An astronaut in microgravity loses that same amount in a single month. Over 7 months of travel to Mars, without a rigorous program of resistance exercise performed for hours each day, a crew member could arrive at the planet with bones no longer capable of withstanding the impact of a landing or a prolonged walk without real risk of fracture. Mars holds roughly 1/3 of Earth's gravity, which means the bones resume bearing load upon touchdown. But only at 1/3 the level they were built for, and after months of intense deterioration, recovery is slow, painful, and frequently incomplete, even with the most aggressive treatment available. Muscles follow the same trajectory through mechanisms that are slightly different. In microgravity, the muscular effort required to perform any task drops dramatically, and the body responds with that same relentless logic. It applies to bone. If it is not being used, why maintain it? Muscle mass can diminish by 20 to 30% over the course of a long mission without intense and continuous countermeasures. Astronauts aboard the International Space Station exercise for 2 hours every day precisely to slow that process. And yet they return to Earth with significantly reduced muscle strength, needing support just to take their first steps outside the spacecraft after months in orbit. On Mars, after 7 months of microgravity, arrival would take place in an environment with 1/3 of Earth's gravity. Less demanding than Earth, but enough to make any physical work utterly exhausting for a body that has lost a quarter of its muscle mass during the journey. The least intuitive aspect of what microgravity does to the human body involves neither the bones nor the muscles, but the head. Without the force of gravity, concentrating fluids in the lower body, the cerebrospinal fluid surrounding the brain and spinal cord redistributes upward, gradually and continuously increasing pressure inside the skull over the course of months. That elevated pressure acts on the eyes from within, compressing the optic nerve and slowly reshaping the eyeball itself from a sphere into a slightly flattened form at the rear. The result, documented in a significant proportion of astronauts who have spent long periods in microgravity, is a progressive deterioration of vision. Some reported being unable to see clearly after months aboard the International Space Station, and imaging tests confirmed structural changes in the eye and optic nerve that, in certain cases, did not fully reverse after returning to Earth. On a mission lasting more than 2 years between Mars and back, this condition would have ample time to develop into something far more severe and potentially permanent, compromising the astronaut's ability to perform precision tasks at the most critical moments of the mission. The cardiovascular system also reorganizes itself in ways that complicate any eventual return. The heart, no longer required to pump against gravity to maintain blood supply to the lower extremities, grows slightly smaller and less efficient over the course of months. Blood vessels lose part of the regulatory tone they need to compensate for changes in the body's position. When an astronaut returns to Earth after months in microgravity, the risk of fainting simply from trying to stand upright is real and well documented. The cardiovascular system has temporarily lost the agility to redistribute blood quickly enough to compensate for gravity acting on the body once more. A return to Earth after years divided between the microgravity of interplanetary space and the reduced gravity of Mars would represent a physiological shock whose long-term consequences we cannot yet predict with confidence. Because no human being has ever traveled that path, the question that seems simplest, why not just bring enough fuel for the return journey, opens one of the most unforgiving equations in all of space engineering. It unlocks one of the most unforgiving equations in all of space engineering. The relationship between the change in velocity a rocket must achieve and the amount of propellant required to do so is not linear. It is exponential. For every increase in the desired velocity change, the fuel mass grows disproportionately because the rocket must also carry the propellant needed to move the remaining propellant itself, a cycle that resets with every calculation. A spacecraft that must decelerate to enter Martian orbit, land on the surface, launch with enough force to escape Martian gravity, brake again to enter a return trajectory, and then travel 7 months back to Earth, requires many times more propellant than a one-way journey alone would ever demand. And that propellant must be carried from Earth at the moment of launch, which means a larger, heavier spacecraft that demands more fuel to lift off, making it heavier still, restarting the cycle in a progression that rapidly transforms any round-trip mission into an undertaking of extraordinary scale, given the chemical propulsion available today. The most developed solution to this problem is to produce fuel on Mars itself, using the resources the planet has available. The Martian atmosphere is composed primarily of carbon dioxide, and there is strong evidence of frozen water beneath the surface and within the planet's polar ice caps. With the right equipment, these resources can be combined to produce methane and liquid oxygen, propellants used in modern rocket engines. The operational concept is to send in advance an uncrewed spacecraft carrying an onboard fuel production facility, allow it to land and produce propellant over months or years, and only then send the astronauts, who would arrive at Mars with the return fuel already prepared and waiting. The theory is grounded in chemistry and physics, established and verified in the laboratory. Executing it at full scale on Mars, under conditions no industrial system has ever faced, is extraordinarily demanding. The fuel factory would need to operate continuously for months at average temperatures of -60 degrees in an environment filled with ultra-fine abrasive dust that carries an electrical charge, causing it to cling to every surface, clog mechanical components, and coat solar panels with a layer that progressively reduces the energy they can capture. Dust storms on Mars are phenomena of planetary scale. Some of them engulf the entire planet for weeks or months, blocking sunlight and drastically cutting the power available to any system that depends on photovoltaic panels, including the fuel factory itself. A single storm during the production period could delay or completely derail the process and the confirmation that sufficient propellant has been produced would need to reach Earth and be verified before the astronauts ever departed, because if they arrive at Mars and the propellant isn't ready or the equipment has failed, there is no return option with the resources on board. The launch window, which determines when the return journey is viable at a reasonable fuel cost, waits for no one. It opens every 26 months, governed by the relative positions of Mars and Earth in their orbits around the Sun, and closes again with the same cold indifference. Missing that window due to a technical failure, a dust storm, a crew health crisis, or any other reason means waiting another 2 years and 2 months for the next opportunity, accumulating more radiation, more bone loss, more psychological deterioration, more wear on the habitat's equipment. Every Mars mission is a sequence in which each phase must perform within expected parameters and where the cost of any critical failure is not merely a delay, but the total elimination of any possibility of coming home. Orbital geometry does not negotiate. The rocket equation makes no exceptions. The physics that determines why traveling to Mars makes returning so extraordinarily difficult is not cruel by design. It is simply indifferent, and that is far harder to accept than any deliberate hostility. 520 days. The approximate duration of a complete round-trip mission to the Red Planet. The experiment was designed to simulate the psychological conditions of that journey without ever leaving Earth, with external communication restricted and artificially delayed to mirror what deep space truly imposes. The participants were carefully selected volunteers who knew exactly what they were doing and why it mattered. And yet, the data collected across those 520 days revealed patterns that the researchers never expected to find with such intensity. As the months wore on, the participants developed what the researchers described as progressive hypoactivity, a gradual reduction in spontaneous activity levels that went far beyond the simple tedium of a confined environment. The volunteers slept more than necessary, moved less throughout the day, communicated less frequently with one another and with the external team. The internal biological rhythm of sleep and wakefulness began to desynchronize in some participants during the later, more advanced stages of the simulation, producing irregular patterns that interfered with cognitive performance on tasks demanding sustained attention. The motivation to complete tasks, even those the participants themselves had identified as priorities and deeply meaningful, declined consistently over time. Something specialists associate not with physical fatigue, but with the prolonged absence of novelty, sensory variation, and spontaneous social contact, compounded by the confined group sharing that same enclosed space. A real mission to Mars would carry all of those factors, plus one that no simulation can ever fully reproduce. The communication delay with Earth, the speed of light, the absolute upper limit for transmitting any information in the universe, imposes a physical constraint that no technology can circumvent, because there is no way to send a message faster than the very fabric of space allows. When Mars and Earth are at their closest, a message takes approximately 3 minutes to reach its destination. When they sit on opposite sides of the Sun, that delay climbs to around 22 minutes in each direction. At any midpoint of a mission, real-time communication is simply impossible. You speak. You wait 40 to 50 minutes for the reply. You respond. You wait again. A conversation that would last 2 minutes on Earth consumes hours of a working day. In practice, communications with Earth during a Mars mission would be recorded messages exchanged asynchronously, like letters, sent through the void of space, stripped of the emotional fluidity and spontaneity that makes contact with a loved one genuinely comforting and restorative. Specialists in the psychology of isolated and confined environments identified a recurring pattern in long-duration missions known as the third quarter phenomenon. The intermediate period of a prolonged journey when the beginning has long since faded away, yet the end remains too distant to serve as any real source of motivation. It is during this phase, documented in polar expeditions, extended submarine deployments, and mission simulation data, that interpersonal conflicts tend to surge in both frequency and intensity. Anxiety deepens, and dysfunctional behaviors become far more likely to emerge, even among individuals who are otherwise psychologically healthy. On Mars, the third quarter would unfold in the most isolated environment any human being has ever inhabited, at a distance where a distress signal takes more than 20 minutes to arrive, and the response takes another 20 to return. The crew members would be the only human beings within reach of one another, without exception and without alternative, under any imaginable circumstance. Every crisis would have to be resolved from within by the astronauts themselves, using whatever resources they had on hand, with no external support capable of arriving in time. What makes this dimension of the problem especially difficult to solve is that no technology can replace human presence as a source of genuine emotional support. And no amount of training can fully prepare someone for what it means to inhabit, for months on end, a place where every problem is, by definition, a problem you must solve alone. This does not make a mission to Mars psychologically impossible. Human beings have demonstrated, throughout history, a capacity for adaptation that routinely surpasses the predictions of every expert who ever tried to define its limits in advance. But it does mean that the people who eventually reach Mars and return from it will not be the same ones who departed. Not only physically, but in the way they understand time, silence, and what it truly means to be close to another human being. And yet, there are people who volunteer. When Mars mission projects were announced with full transparency about the risks involved and the very real possibility of not returning immediately, the number of applicants reached into the tens of thousands. These were not impulsive people, nor were they lost souls searching for meaning. They were engineers, doctors, scientists, teachers, and students with deep personal bonds, clear life plans, and a secure future here on Earth, who read every requirement with care. They understood exactly what was being asked of them, and they signed up anyway. This phenomenon does not fit neatly within the logic of self-preservation that normally guides human decision-making, and it says something profound about what we are as a species, something that reaches far beyond any conventional psychological analysis. The combination of accumulated radiation, progressive bone loss, radical isolation, delayed communication, and uncertainty of return was not enough to diminish the interest. For many of these people, the weight of not going was greater than the weight of every risk combined. The history of human exploration is filled with journeys undertaken without any guarantee of return. The first ocean crossings were made in vessels that had no way to call for help if something went wrong 1,000 kilometers from shore. The polar expeditions of the early 20th century set out with incomplete maps into regions where any rescue was physically impossible. What sets Mars apart is not the nature of the risk. It lies in the precision with which that risk can be calculated with foresight. And yet, that is still not enough to dissuade. Never before has a human being been able to know so clearly, so quantitatively, what awaits them. The radiation dose, accumulated month by month, the projected bone loss week by week, the exact communication delay at each phase of the mission, the statistical probability of failure for every critical system. To know all of this with such precision and still choose to go is not courage born of ignorance. It is courage in spite of knowledge, which is, by any available measure, a far rarer and more extraordinary form of human resolve than any historical adventure that came before. What this picture reveals about the future of any human presence on Mars is far more nuanced than the list of obstacles suggests at first glance. A round-trip mission using current technology would demand simultaneous advances in propulsion, radiation shielding, space medicine, and psychological support, all of which are still in active development. But a mission of permanent presence, where the commitment is to build something on Mars with no expectation of immediate return, as a first generation of true inhabitants rather than temporary visitors, confronts a different set of problems, some of which are far less intractable. Without the need to carry return fuel, the available payload increases significantly. Without the pressure of a return deadline dictated by the orbital window, there is time to build infrastructure at a more sustainable pace. What does not change in any scenario is the physical and psychological demand that Mars imposes on every human being who arrives there. And the central question ceases to be whether it is possible to go and becomes instead what kind of person accepts that agreement with full knowledge of what it entails. There is a question this scenario raises inevitably, and it is not rhetorical. If you had the real opportunity to be part of the first human generation to live permanently on another planet with clear knowledge of every risk, with a community of companions, with the mission of building something that has never existed before in the history of the species, would you consider that choice? Not as a distant fantasy, but as a concrete possibility being developed right now, with technology being tested right now, by people training for it right now. Leave your answer in the comments. What would be the greatest obstacle for you? The radiation? The isolation? The permanent transformation of the body? Or simply the distance from everything and everyone you love here? The way each person answers that question reveals priorities and values that exist within them. Most of us never have to name them any other way in the course of everyday life. What Mars teaches us in the end is not about the hostility of the cosmos, nor about the limits of engineering. It is about the nature of the impulse that brought us this far. The same impulse that drove us to cross oceans without maps, descend into bottomless caves, and gaze at the sky with the intention of going there. The same species that has yet to solve its most basic problems is also the species that looks at a hostile planet tens of millions of kilometers away and thinks, I want to go, and I am already calculating how. If this video found its way to you, share it with someone who would ask themselves the same question. Because few conversations are more revealing than this one. And if you want to keep exploring the universe with that same honesty about what we know and what we are still discovering, subscribe right here. There is so much more. Coming soon.